Yo, what's up, Sci fam? It's your boy Nickel. Today, let's learn about Newton's third law of motion. We'll define that law of motion, and then we'll also learn about free body diagrams and how they help us to really emphasize and understand Newton's third law of motion. All right, so let's begin here by defining Newton's third law of motion. Isaac Newton stated that for every action, there is an equal and opposite reaction. So we'll dig into exactly what that means. But if I were to just break it down real simply for you, it means like AKA that, or also known as, that for every action there's an equal and opposite reaction, that forces, pushes, and pulls actually come in pairs. Now you could probably understand this because if you push on the wall, you can feel the wall kind of like pushing back on your hand. It's not like the wall moves to push on your hand, but your hand feels something when you push on the wall, even though you're the one pushing on the wall. So forces, they come in pairs, and there's two qualities about them. It's up there in that definition, but we'll go ahead and write them here to kind of really emphasize the fact that they are going to be equal. They're going to be equal in size. The harder you push on the wall, the more you feel it on your hand. If you try to karate chop the wall, you're really going to feel it on your hand. So it's equal in size and opposite in direction. Even though you are applying force to the wall is applying force in the opposite direction back onto your hand. So that's just a simple example there. That to understand Newton's third law of motion, we have to understand the fact that for every action, there is an equal and opposite reaction, or forces come in pairs. All right, so to really be able to understand this, there's this really handy tool in physics, and these handy tools are called free body diagrams. And the reason is because you can see this complex situation down here. It's not really that complex, but on my green shag carpet here, there's a table, and that table is holding an apple. Now, we don't want to look at this whole system or have to draw this every time we're talking about how the apple is sitting there on the table. So instead, we're going to free the apple from the table and look at the forces that are acting just on the apple. So free body diagrams means that you're going to remove the item from its overall complex situation. So free body diagrams are used to show the forces that are acting on an object. So instead of showing the object in its full complex scenario, we want to free it up. Now, in order to understand how we're going to actually draw a free body diagram, there's a couple rules that we need to follow. First is that the object, in this example, it's going to be the apple, is going to be represented with a square. Or you could say a box even. So go ahead and do that over here. Let's draw ourselves our first free body diagram by drawing ourselves a square. Okay. The next thing we need to do is inside that square, I like to draw a little dot here to show where the middle of that square is. Because now we're going to draw some arrows. And we're going to have arrows on our free body diagram box here to understand what's happening to this apple. So right now the box, that square, represents the apple. It's much easier to draw a square than an apple. So we're going to draw the square. Now we're going to add some arrows. And arrows are going to be used to show the forces that are acting on the object. So if we look up at our apple here, we can see, well, the apple is just sitting there on the table. So that means that this apple must have some weight due to gravity. So there's this downward force of gravity. So we are going to need to show that in our box here. So in order to show that, we need to understand one thing that's important, and that's that arrows always start from the center. So to draw my first arrow here, let's change the color so you can see what's happening. I'm going to draw the arrow of the downward force. The downward force is going to be the weight of the apple, and that has to do with the amount of gravity. If we were on the moon, that arrow would be shorter because there wouldn't be as much gravity pushing the apple down onto the table, and the apple would have, quote unquote, less weight. So that downward arrow is the force of gravity. And I might forget that, so let's go ahead and write the actual name on that arrow. Your arrows always must be labeled. Maybe we should add that here as one of the rules. Always have labels on all force arrows. So every time you draw an arrow to show the force, you must label it. All right, so arrows show forces acting on the object. They always start from the center. And when we look at those arrows, the size of the arrow is going to represent the strength and the direction of the force. So I drew that arrow in the downward direction on this square to show that the weight is in the downward direction. The size of the arrow, as I said, would be shorter if we were on the moon because there's less gravity. So that would show there's less force in the downward direction, but we're not. We're on Earth, so we're going to keep it in that same size. So the strength of gravity is represented by the arrow and the length of the arrow. The direction is also important here because it's holding it down on the table. Now this free body diagram right here, right now is actually showing that the apple is falling through the table because there's nothing equalizing that downward force. So it would just show something that's falling because there's only one arrow in the downward direction. But as Newton says in his third law, forces come in pairs. They're equal in size and opposite in direction. So for every action, there's an equal and opposite reaction. So even if it's just simply an apple sitting on the table, well, luckily this table has enough force to actually be pushing back up on the apple. If it didn't, imagine if that was just like a piece of ice, a really, really thin piece of ice. And you set a heavy apple on it, it might break right through and you'd have a broken ice table. That didn't happen though. So let's get a new color here to show that in the upward direction, since this apple's not moving, it's going to be actually equal in size and opposite in direction. And this is just simply the force of the table. So you can see that this free body diagram is much easier to draw than the table, and it allows us to show the different forces acting on the apple. We have the weight of the apple in the downward direction, and we have the force of the table in the upward direction. And since these two arrows, if we draw them side by side, we would see that these two arrows are actually the same size. They're opposite in direction, but they're equal in size. And this means that they are balanced because they're equal in size. And when things are balanced here, it means that there is no motion happening. And well, that's true. We just have the apple sitting on the table. So let's use all these rules here for free body diagram to do one last free body diagram of our alien. So again, we need to start. I'll just use some new colors to just show it doesn't matter what color we use, but we start by drawing the alien as well. Yeah, just simply a square with our little dot in the middle. Now this one's a little bit more complex. Here we have an alien who is leaning on a brick wall. Now the wall is staying nice and strong there. So let's think about the different forces that are acting upon it. Now since we have our alien and it's here on Earth actually, this is Earth because we have a brick wall. I'm telling you it's Earth. So we have gravity. We have the weight of the alien. So let's first draw a downward arrow to show this is the weight of the alien. And again, we need to label our arrows every time. Well, as I said before, a one down arrow would mean that that alien is currently falling, but it's not. It's actually just hanging out there on the ground. So therefore, what's happening is that there's actually the ground here. And the ground is holding the alien up. The alien's not falling through the ground. It would, if it was water, that alien would fall right through it. But the ground has enough force. And like Newton said, forces come in pairs. So there's an equal and opposite force, and this would be the force of the ground. So make sure that you label these arrows because we need to remember what they are. Because we won't have that picture, that beautiful picture of the alien. You might not actually draw that in there. You could draw it in to show what cool thing you're representing here, but we're doing the free body diagram. So if we have the labels on there, you'll probably remember exactly what you're drawing. Now, like I said, this alien is leaning, which means that the alien has some backwards force. Has some backwards force on the wall. And so this could be the force of the leaning. Now, just like Newton said, for every action, there's an equal and opposite reaction. So if that alien is currently leaning on the wall, this free body diagram right here would show that the ground's holding the alien up, the weight is holding the alien on the ground, that the alien's falling through the wall because there's no opposite force balancing it out. But that's not what's happening. So what's happening is that the wall is actually pushing back on the alien with equal force. And just like, if these were just cardboard bricks stacked up on top of each other here, they would tumble like Jenga blocks if this alien were to lean on these bricks. But that's not what happened. The wall is holding the alien up. So therefore, the wall is pushing back on the alien and keeping the alien in place. So we can say this is the force of the bricks. And it's pushing back on the alien. So you can see that these free body diagrams are going to be a way we can represent Newton's third law of motion, that for every action, there's an equal and opposite reaction. For if you're leaning on a wall, the wall is actually pushing back on you. Kind of a weird way to look at the world. When you step on the ground is pushing back up on you. Whoa. All right, I'll blow your mind again in the next Science Notebook Page video. See ya.